Hey there and welcome to this video. Today we are going to implement a pretty cool reinforcement learning paper called the Sensory Neuron as a Transformer, Permutation-Invariant Neural Networks for Reinforcement Learning. This is the official GitHub repo, the author is open sourced, and it contains both training and evaluation scripts together with pre-trained models. The implementation I prepared for this video is heavily inspired by this repo, however I decided to only focus on a single task, the CartPoleSwing up. The official code is way more general since it can handle all the tasks described in the paper. Anyway, in my opinion, implementing the attention neuron for the CartPole task should be enough to understand the most important concepts. As always, all the credit goes to the authors, and I just want to stress that I'm not affiliated with any of them. Finally, I apologize in advance for potential misinterpretations of their work and bugs in my code. One thing I would like to highlight is this amazing and interactive website that the authors created. One can experiment and play around with the pre-trained models, and I will use it later to explain some important concepts. Let me try to explain in my own words what the paper is about. I would definitely recommend you to stop the video here and go read the paper to have more context. First and foremost, the authors want to create a permutation-invariant policy network. What does it mean? Well, it simply means that no matter how we shuffle the input features, the output action is going to stay identical. The second goal is related to the first one, and it is to have a single function that processes each feature independently. Here I name this function flocal. And it is only after this independent processing that we try to combine the local information into a global picture using the fglobal function. In the next couple of slides, I'm going to discuss the exact architecture of the policy network. However, let me just point out that the paper actually demonstrates two very interesting things. First of all, one can actually successfully train agents like this, and they work pretty well, which is in my opinion not obvious. And second of all, agents trained like this seem to be immune to noise, which I find pretty surprising too. Anyway, let us now focus on more specific things. As mentioned before, to make things simple, both these slides and the code are going to assume that we are dealing with the CartPoleSwing up environment. The policy network has two inputs. The first one is the observation vector, or I will sometimes refer to it as the feature vector. It is composed of 5 real numbers: the position of the card, the velocity of the card, the cosine and the sine of the pole angle, and finally the angular velocity. At each time step, we will get a new observation vector from the environment. The second input is the previous action, and it represents the force we apply to the card. Our objective is to take these two inputs and define a function, or more specifically a neural network, that is going to turn them into a new action. Here you can see the entire pipeline of the most important steps to get from the inputs to the output. First of all, we apply element-wise functions to the inputs. This is in line with the locality requirement that I talked about. And then we generate 3 new matrices, Q, K, V, which stand for query, key, and value. And they are going to be used in an attention module. And what comes out of this attention module is a latent code, which is going to store all relevant information about the observations and the previous action. And finally, we will take this latent code and just run it through a linear module to get the final prediction, which is the new action. Regarding the terminology, this entire pipeline describes the forward pass of our policy network, and everything before the linear module is called the attention neuron layer. So how do we create the attention inputs? Before I start explaining them, let me just point out that in the top right corner, you can see the variable names that we are going to be using in the code, plus their actual values that were taken from the paper. Anyway, let's start with the easiest one, which is the value matrix. It is going to be equal to the observation vector. Also, I added an extra dimension to it so that we can use it in matrix multiplications. Then we will have the query matrix, which is actually not going to contain any learnable parameters, and it will just be the so-called positional encoding. If you're not familiar with it, it is a way how one can encode the order information, and it is used heavily in natural language processing. The even columns are just sine functions with decreasing frequency, whereas the odd columns are cosine functions with decreasing frequency. Lastly, we want to create the key matrix. It is basically motivated by two ideas. First of all, we want it to depend both on the observations, but also on the previous action. That is why we concatenate these two. Second of all, at a fixed time point, we would like to not only have access to the most recent observations and the previous action, but ideally also all the previous observations and actions that we gathered during our current episode. And in a way, this can be achieved by keeping a hidden state for each of our features. Then we have an LSTM cell that takes in the previous hidden state and the new observation and action and spits out a new hidden state. And that is exactly what you see on the screen. Let me just stress that the LSTM cell has learnable parameters which are shared among all the features. Anyway, the K matrix is nothing else than the output hidden state of our LSTM cell. Here you can see the attention computation together with the shapes of the matrices. We take the query matrix and the key matrix and project them in a linear fashion, and then we just multiply them. The way you can interpret this is that for each row of the query matrix, we want to know what the most similar rows in the K matrix are. And after we scale these similarities and run them through the hyperbolic tangent activation, we get attention weights. And finally, we multiply the attention weights and the value matrix to get our latent code. Let me just stress two things. This attention computation will work out for any number of features, and the final latent code size is dictated by the number of embeddings. This means that our model will be able to accept feature vectors of arbitrary size. Second of all, if we disregard the fact that each feature could have a different hidden state, this entire pipeline of going from the observation to the latent code is permutation invariant. And finally, we take this latent code and we apply a linear module to it, and we get our final action. And since this latent code was permutation invariant with respect to the observation, this new action is also going to be permutation invariant. Also, let me point out that in theory, we could replace this linear module by something more complicated like the multi-layer perceptron. However, a linear module should be enough to make a good model. And yeah, that is basically all we need to know about the policy network. Alright, so let's start coding. So first of all, we want to implement our neural networks in PyTorch and write some utilities. Alright, so before we start implementing the fancy permutation-invariant network, let us just create a benchmark network that we are going to use for comparison. More specifically, let's just create a multi-layer perceptron. Alright, so we specify the number of features, and it is something we need to know in advance. Hidden layer sizes is just a tuple of integers representing how big the different hidden layers are. And internally, everything will be actually stored in this sequential module. So here we define a new tuple containing all the layer sizes. So we start with the 0th layer, which is, let's say, just the feature vector. And finally, we also append this output layer, which has just one element, and that is because our action is just a real number. And here we iteratively define a bunch of linear modules followed by the hyperbolic tangent activations. We unpack all the layers into the sequential module. This part is definitely not standard because what we are doing is taking all the parameters that our network has and we are telling Torch that we don't care about the gradients. And this is actually something proposed in the paper because the author suggested that for the CartPole task, the best approach is to do a so-called direct policy search and use an evolutionary algorithm that doesn't need gradients. So in other words, we only use Torch to define conveniently the forward pass. However, we don't care about its autograd functionality at all because we won't use gradients for the optimization. The input to the forward pass is just the observation tensor. Let me just point out that one difference to, I guess, standard deep learning code is that we don't necessarily work with tensors that have the batch dimension. And that is because when we roll out the task, we will only have access to one single step at a time. The output is nothing else than the action. And the actual implementation is just a one-liner. What we do is that we temporarily prepend the observation tensor with the batch dimension so that it's compatible with Torch. We run the forward pass of our network, and finally we only extract the first sample in a batch because that was just a single sample. Two small comments. In theory, we could have also included the previous action as one of the inputs, but whatever. And the second thing is that we are guaranteed that this return value is going to be in the interval -1, 1. because we apply the hyperbolic tangent activation. And now we want to start building all the different components of the attention neuron. Let's start with the query tensor, and as discussed before, it is going to be the positional encoding. Alright, so it depends on two parameters. The first one is the number of embeddings, which is just the number of rows of our table. Then the hidden size, which is just the number of columns. What we return is a NumPy array that represents the positional encodings. For your convenience, this is the formula. This is just a helper function that is going to compute the angle. And this helper function is basically just constructing a row in our table. We define the entire table of angles row by row. We apply the sine function to all the even columns and the cosine function to all of the odd columns. Let me just stress there is nothing learnable about this table, and it only consists of constants. Anyway, this is exactly how it's going to look like. We have 16 rows and 8 columns. Now we would like to implement a module that is going to compute the attention matrix using the key and the query tensors. So first of all, we need to provide the projection dimension. We have to provide the hidden size, which is equal to the number of columns of both the Q and K tensors. And finally, we can choose whether to enable or disable scaling. Internally, the projections will be done using the Torch linear module, and we'll have a separate one for both the key and the query tensor. So we instantiate two linear modules and we set the bias equal to false. And we also prepare the scaler. Alright, so the forward pass will accept two inputs. The first one is going to be the query tensor that has the shape of number of embeddings times hidden size. And the second input is going to be the key tensor of shape number of features times the hidden size. We then return the attention weights that are of shape number of embeddings times number of features. And what's a little unusual is that they won't sum up to 1 in general, because we are going to use the hyperbolic tangent activation rather than the softmax. By the way, this is the exact formula that we're trying to implement in the forward pass. Here we project the query tensor. Here we project the key tensor. Here we matrix multiply both of the projections. We divide by the scalar, and this division is element-wise, so it's not going to change the shape. Finally, we apply the hyperbolic tangent activation. And again, it's element-wise and it doesn't change the shape. And that's it. And now we can finally start putting things together. Let's implement the entire attention neuron module. We provide the number of embeddings, which is a hyperparameter, and this will actually end up being the length of our latent code. And then we provide more hyperparameters, namely the projection dimension and the hidden size. Internally, we will have this hidden state, and know that it is going to be specific to LSTM, which means that it's actually two tensors. And then we will have this LSTM cell module, and as discussed, it's going to be used to create the key tensor. Then we will have an instance of the attention matrix module that we just implemented. And finally, we will have this buffer that is going to hold the query tensor. Here we store the parameters as attributes. We initialize the hidden state with none, but as you will see in the forward pass, this will basically mean that we will populate it with zeros. Here we instantiate the LSTM cell. So the reason why the input size is 2 is because we will concatenate one element of our observation vector, for example, the position of the card with the previous action. We instantiate the attention matrix. If you're wondering why we set scale equal to false, which we know means that we will just divide by 1. If I'm not mistaken, this is what the authors did in their code. So I just used the same logic. And here we use the utility function that we rolled, and we generate the positional encodings. We convert them to a torch tensor, and finally we register it as a buffer. So similar to the multilayer perceptron forward pass, we see that we provide an observation, and again, we are not working with tensors that have the batch dimension. Additionally, we also provide a number representing the previous action. What the forward pass returns is latent code, which has a shape of number of embeddings, and it also outputs the attention weights in case we want to inspect what happened inside of the attention. Here you can again see the formula for computing the key, and it will be nothing else than a new hidden state. Anyway, just to avoid confusion, the H and C hidden states that you see in this formula will be grouped together in the code into a single tuple called HX. Here we just concatenate our observation tensor with the previous action. In case the hidden state was none, or in other words, if this is the first time we run the forward pass, we populate both of the hidden states by zeros. And here we call our LSTM cell. Here we create a variable for our query, which is nothing else than the internal buffer. The K tensor is nothing else than our output hidden state. The value tensor is nothing else than the input observations, or we just add a new dimension to it so that it's easy to do matrix multiplication. And here you can see the exact formula to generate the latent code. Here we call our attention matrix module and we get the attention weights. Finally, we matrix multiply the attention weights and the value tensor. And by the way, we again applied the hyperbolic tangent activation. It's not something I showed in the formulas, but again, I think I saw it in the official implementation. So I just applied the same activation. We squeeze out the dummy dimension and we end up with a one-dimensional tensor, which is our latent code. And we return it together with the attention weights. And yeah, that's it. Let us just play around with the attention neuron module. We defined all the important hyperparameters and we want to instantiate our module. First of all, let me demonstrate that our module doesn't care about the number of input features the observation vector has. We iterate through different number of features and we always make sure that we set the hidden state equal to none. And as you saw during the first forward pass, it will be actually populated with tensors of zeros. So we actually want to reset it. Here we set 0.5 as the previous action, and we generate a random observation vector with the corresponding number of features. The shape of our latent code is always 16, which is the number of embeddings, and it is independent of the number of input features. This is definitely a very cool property of the attention neuron. Second of all, let us look into the permutation invariance. Okay, so I create an observation tensor with 5 features, which is in line with the CartPole task. Again, I make sure that we always reset the hidden state, which is equivalent to just starting a new rollout or episode. Here I generate a random permutation. And then we actually permute the observation tensor and send it through the attention neuron. In all three of the cases, the latent code did not change. So in other words, if the hidden state is identical between different calls, then yes, the permutation invariance will hold. However, let us try to remove the resetting. And here you can see that if the hidden state is not normalized, you will get different latent codes. And just to kind of illustrate the point, I'm going to use the interactive website the authors created. So let us see what happens when we click on the Shuffle Observations button. As you can see, it clearly disrupted the performance of the model. However, after a couple of steps, the model is back to working perfectly. Shuffling the observations actually does have a temporary effect on the performance of the model because unfortunately the hidden states cannot be shuffled or permuted accordingly because we don't know what the ground truth permutation was. However, it seems like after a couple of steps, the hidden states are correctly updated too. All right, and there is one more thing to do, and that is to create the entire policy network. Here again, we have the three hyperparameters, exactly the same ones as for the attention neuron module. And internally, we will have an instance of our attention neuron module and also an instance of a linear module. We instantiate the attention neuron. And we instantiate our linear layer that is going to input the latent code and output the new action. Here we do exactly the same thing as we did with the multi-layer perceptron. We disable gradient computations for all our parameters. So the inputs to the forward pass are exactly the same as for the attention neuron. It's the observation vector and it is also the previous action. And the output is the next action. We run the forward pass of the attention neuron. We take the one-dimensional latent code, we temporarily add a new dimension to it so that it's a batch of a single sample. We apply the linear layer, and finally we apply the hyperbolic tangent activation. And here we just get rid of the batch dimension. So we have written our deep learning modules and our goal is to turn them into reinforcement learning agents and ultimately train them. However, this will require some extra code that some of you might find boring. So I definitely encourage you to check out the chapters that I provided for this video and skip all the way to the end where I discuss the results. Anyway, if you're staying, let's go back to coding. To make things more readable and extendable, we are going to introduce a concept of a solution, which is just a unified high-level interface, and its goal is to hide all the lower-level details related to Torch modules. We are going to create an abstract class called solution, and the idea is that we are going to subclass it twice, once for the Permutation-Invariant Network and the second time for the multi-layer perceptron. Alright, so first of all, we make an assumption that the solution has an attribute called policy that will actually store the Torch module. Here we define an abstract method. What it means is that the child will actually have to implement this. This specific method is called clone, and its goal is to copy the current solution. The goal of this abstract method is to get the next action given the current observation. Alright, so this method is supposed to return the number of features the model expects, and we will have a convention that if this method returns a none, then it means that it can take in an input of any size. Because as we saw, it doesn't matter how big the feature vector is, whereas for the multi-layer perceptron, it will be a fixed number. So this method is going to reset the solution, and the specific use case is going to be resetting the hidden state of the Permutation-Invariant Network. And later on, we will make sure that this method is called at the beginning of each rollout. First of all, note that this is not an abstract method anymore, and the reason for this is that we will provide an implementation in this parent class. Its goal is to get all the learnable parameters our neural network has and flatten them into a one-dimensional array. Here we iterate parameter by parameter. We cast the torch tensor to a NumPy array, and finally we flatten this array. And as you can see, I'm not necessarily sending this tensor to a CPU because in this video and in this code, we're going to assume everything takes place on a CPU, which by the way is a simplification, and I think the original code also kind of handles possibility of running the forward pass with GPUs. And finally, we concatenate all the 1D arrays into a single huge 1D array. And the reason why this flattening needs to take place is because we are using, let's say, a black box evolutionary strategy that I will discuss later. And it doesn't really care about the fact that some parameters come from a linear module or some other come from the attention module. There is no structure. All right, so we implemented the getter, but we also want to implement the setter. This method is going to take in a 1D NumPy array of all learnable parameters, and it's actually going to go inside of the neural network and just assign all these parameters to the corresponding weights. We're going to keep track of what the starting index is and what the end index is. And then we're going to take the torch tensor and we're going to redefine it in place using the user provided parameters. Finally, we just update the start index. And again, this method is going to be used in the optimization because we will have this black box optimizer that is at each iteration going to suggest multiple different parameter sets. And we will just want to evaluate how good our network is given these parameters. And finally, just a small method that counts up the number of parameters. And yeah, that's it for our abstract class. Let us now subclass the solution class and create a multi-layer perceptron solution. So we provide the same hyperparameters as we saw before, and internally we'll store all the hyperparameters and also the actual policy network. Here we store the hyperparameters and we also define the D-type to be float32. We instantiate our multi-layer perceptron module, we cast all the parameters to the float32 D-type, and finally we set it to evaluation mode. Here we define what cloning means. Here we take the observation, which is a NumPy array. We cast it to torch tensor. We make sure it has the right D-type, and then we run the forward pass. The number of features is going to be fixed. And finally, the multi-layer perceptron solution will not have any resetting logic since there are no hidden states. Now we want to create a second child class, and it's going to be the Permutation-Invariant Solution. We've seen these hyperparameters before. Again, we will store all the hyperparameters in this dictionary. We will have our policy network, which is the Permutation-Invariant Network. However, what is different to the MLPSolution is that we will also store the previous action internally. That means that whenever we call the get action, the previous action will get updated. We instantiate our policy network. Finally, we initialize the previous action to 0. This call method is actually identical to what we did with the MLPSolution. I guess we could have put it in the abstract class. So to get the action, first of all, we convert our NumPy observation array to a torch tensor. Then we also provide the previous action, which we are storing internally, and then we just run the forward pass of the policy network. Here we make sure that we update the previous action with what we just predicted, and we also return this action. So unlike the MLPSolution, here we actually implement the reset method. There are two things that are happening. First of all, we make sure that the hidden state of our policy network, or more specifically of the Attention Neuron submodule of the policy network, is set to none. That means that we are kind of deleting all the memories. And second of all, we set again the previous action to 0. Finally, the number of features is going to be none. This will mean that the number of features can be anything we want. Anyway, now we would like to actually implement the rollout logic using the OpenAI gym and the CartPoleSwing up environment. The authors actually use their own implementation of this task, which is supposed to be harder since the initial state can have more extreme values. However, I did not really want to rewrite it from scratch or clone their repo, and instead I just tried to look through GitHub for similar implementations. I found this repo, which seems to implement more or less the same thing. However, it seems to be an easier version of the CartPoleSwing up environment, but it is not that big of a deal. The author put it on PyPI, which is great, and we're going to use it. So let us quickly implement the rollout logic. Here we just define the number of original features constant, which is 5. It's mostly for convenience. So here we define a custom exception, and we're going to raise it in case the model number of features is not equal to the actual number of features inside of the observation. First of all, we can choose whether we want to render the environment or not. This shuffle and reset flag will give us an option to randomly shuffle the features at the beginning of each episode. And this is actually the way how we're going to test whether our agent is able to deal with shuffled features. Let me also point out that the authors investigated the possibility of shuffling during the rollout rather than just before we actually run the rollout. And yeah, our code is not going to contain this possibility. The number of noise features will control how many noise features we will inject into the observation vector. And the main use case for this is to really test out whether our permutation invariant agent is immune to noise. Then we have 2 different random states. Finally, we have the maximum episode steps. By the way, in this video, I use the words episode and rollout interchangeably. Internally, we will store the number of overall features, which is the original ones plus the noise ones. We will have this numpy array that is going to hold the permutation indices. Also, we will have the actual gym environment. Here we make our environment. Here we redefine the maximum episode steps. For the rest of this video, the number will be always 1000 because that's what the authors used in the paper. The number of overall features is the original features plus the noise features. Here we just create a range of integers from 0 to number of features. And this array will be actually used for the shuffling. Here we set the noise standard deviation to 0.1. I just took it from the paper. And when we are actually injecting noisy features inside of the observation, it will always come from a Gaussian distribution with mean 0 and this standard deviation. Now we want to define a method that will dictate what happens just before the rollout. The only thing we actually do before the rollout is to make sure we permute the features. Here we regenerate the permutation indices to be again a range of numbers, and then if the user wanted to do the shuffling before each rollout, we just shuffle it. And know that this shuffle method actually works in place. First of all, we actually want to shuffle the features. And second of all, if the user wanted to have noise features, we will insert them into this array. The input is the raw observation feature array that only has 5 elements. This is actually what the gym environment is going to give us at each step. What is returned is a modified version of the input. It will be shuffled and it will contain noisy features. And this modified observation is exactly the one that goes on to our deep learning model. Here we use the normal distribution to generate our noise vector. Here we concatenate the original observation vector together with the noise. Here we use our permutation indices to do the shuffling. Alright, and now we have everything to actually implement the rollout. The input is going to be the solution, so it's either the MLPSolution or the Permutation-Invariant solution, and we return a reward representing how good of a job our solution did during this given rollout. Here we just wrote a check making sure that the number of features is compatible. First of all, we run the reset for rollout that we just implemented, and as you saw, this will do the shuffling of the permutation indices, assuming the user wanted to shuffle. Now we will reset the solution, and if you don't remember, it was a no-op for the MLPSolution. However, for the Permutation-Invariant solution, this would set the hidden state to none, which means that we basically forget everything that happened. And lastly, we also reset the gym environment, and this will give us the very first observation. Optionally, we also render. So this episode reward will be the return value, and we will actually iteratively add to it all the per step rewards. Done is a boolean that will signal whether our rollout has finished or not. And there are two ways how we can finish. The first one is reaching the maximum episode steps that we set to 1000, or the second option is that the cart goes off the screen. We modified the raw observation, which means that we will add the noise features to it and we will shuffle it. We send this modified observation through to our solution to get the next action. We call the step method of the gym environment, which accepts the new action, and it gives us the new observation, a reward, and it updates the done variable. And that's it for our rollout. But again, as I mentioned, we're not able to shuffle during the episode, but only before the episode. Before we start writing the training script, let me quickly talk about the actual optimization algorithm we are going to use. It is called the Covariance Matrix Adaptation Evolution Strategy. And what you see on the screen is a Python package that implements it. And I'm not sure why the authors decided to go for this specific optimizer. However, we're going to use the same thing. More specifically, we will be using the ask and tell interface. The idea is that at each iteration, we will ask the optimizer to give us a set of candidate parameter vectors. And we are then responsible for actually assigning a loss to each of them. And once we have it, we will just tell the optimizer what the losses are. All right, so let's implement the training script. So first of all, let us write a save function that we will call during our training. We simply create a tuple with two elements. First of them is going to be the solver instance, and second of them is going to be our solution instance. Then we just pickle dump it on the disk. And now the goal is to write a getFitness function that is going to evaluate how good or bad a given solution is. So this function is going to input a solution and also a couple of other task-related parameters, and it is going to return a list of all episode rewards. And we will need to run this function for each of the proposed parameter vectors from the optimizer. And the actual implementation is pretty straightforward because all the logic is actually implemented already inside of the task class. Now I'll quickly write a CLI. All right, so let me discuss a couple of important arguments and options. So the first positional argument is named solution, and there are three options: linear, MLP, invariant. In the background, what we want to do, we want to instantiate the corresponding solution class. And note that linear is nothing else than multi-layer perceptron with no hidden layers. And this logging folder is where we're going to put all the Tensorboard related records and also the checkpoints. This parameter is very important because it determines how many rollouts we will do when evaluating the fitness. The higher this number, the more precise estimate we will have. However, the slower the training is going to be. I took 16 because I believe that's what the authors did. Also, we will implement a multiprocessing logic, and here one can specify the number of jobs. Here, another optimization related parameter, which is the population size, and by default it is set to 256, and it basically dictates how big possible solution set is going to be at each iteration. I think the reason why the authors put it to 256 256 because they had a cluster that had 256 CPUs. Again, we'll just set it to the same number. And finally, we can shuffle on reset during the training, and we'll actually use it in some experiments to kind of see whether one can improve the multi-layer perceptron if at training time we do this shuffling. So in a way, it'll be like augmentation. We instantiate the Tensorboard summary writer and we dump all the parameters. And now we just want to map the string solution to an actual solution instance. First of all, we define the linear solution, which is nothing else than a multi-layer perceptron with no hidden layers. I know that here we need to specifically mention the number of features at training time. Here we create a multi-layer perceptron with a single hidden layer size with 16 nodes. Finally, the star of the show, the permutation-invariant solution with these hard-coded hyperparameters, but as mentioned, these are the hyperparameters they used in the paper, I believe. Now we would like to initialize our solver. There is an option of providing a checkpoint that is useful for continuing training that was started before. If there's no checkpoint, our initial guess is going to be just zeros. Then we just simply instantiate the solver, providing all the relevant solver parameters. However, if the user does provide a checkpoint path, we unpickle it. All right, so now we just take our getFitness function and we set all the keyword only parameters. All right, and here, if the number of jobs is -1, we actually want to use all the CPUs, and if not, it's just whatever the user provided. Finally, after all this work, we can write the training, or let's say evolution logic. First of all, we use this multiprocessing pool context manager to be able to do multiprocessing in a very simple way. Then we will iterate all the way up to the max number of iterations. And here we ask the solver to give us a bunch of different proposals when it comes to parameter vectors. And actually the size of this param set is going to be equal to the population size. What we do in this iterable is that we go one by one through the parameter vectors, and we just use our setParams method of the solution class to actually register those parameters. So we basically go through each solution in our iterable and we just compute what the fitness of that given solution is. And remember, our getFitness function was actually returning a list of per episode rewards, and here we just actually consider the mean of these as the final fitness of that given solution. And since the CMA solver actually looks for minimums, we need to flip the sign. And here we will just concatenate all the parameters together for evaluation purposes. And yeah, here we have a bunch of useful metrics. And here we'll basically checkpoint our model and the solver every couple of iterations, or if it's the very last iteration. Finally, we actually tell the solver how good or bad the proposed parameter vectors were. If we send the keyboard interrupt signal, the checkpointing will take place. And yeah, and that is our training script. All right, I wrote a script that launches multiple experiments. First of all, we train a simple linear model and there is no shuffling taking place during the training. Then we train a linear model again. However, this time we're going to randomly shuffle the features before the rollout. And that means that the fitness function should basically encode how good the model is when we give it randomly shuffled observations. This approach is very reminiscent of augmentations, and instead of encoding a certain prior into the architecture, we want the model to learn permutation invariants from data, or at least partially. The third and the fourth experiment are the multi-layer perceptrons with and without shuffling. And finally, we have our permutation-invariant solution. And let me just stress that at training time, we are not going to do any shuffling whatsoever. Also, you probably noticed that the number of iterations for the permutation-invariant model is very high. And let me just warn you that unless you have dozens of CPUs, you will not be able to train it. It is totally possible that my modifications to their code introduce major slowdowns. Anyway, it is what it is. I actually ran this entire script already, and let me just show you the results. Okay, so here we have the Tensorboard, and let me show you some plots. Let's look at the max generation metric. So each iteration, or let's say generation, the solver proposed 256 different solutions. And this graph basically shows the best solution per generation. Let me just stress that the upper bound of this metric is 1000, which would mean that we held the pole completely straight for 1000 steps. However, since the environment starts with the pole being down, it is virtually impossible to actually reach this upper bound. Here you can see the 5 different experiments, and clearly the multi-layer perceptron model corresponding to the red plot without augmentations was the model that was able to solve this task, and it didn't really take it that many iterations. The linear model in dark blue did not seem to have enough capacity to learn the tasks perfectly. However, it almost hit the 800 mark. The orange plot is the permutation-invariant agent, and as you can see, it keeps on going up, however at a very slow rate. I'm sure if I continued the training, it would get to higher scores. However, running these 9,000 iterations already took more than a week on my machine. Finally, if we look at the pink and the bright blue experiments, they were not really able to hit very high scores. Note that these experiments correspond to the augmentation setup where we were shuffling before each rollout during the training. Anyway, the metrics we were tracking with Tensorboard are interesting. However, the main question we want to answer is the following. How good are these models when we shuffle the features before each rollout? And what happens if we inject noise features into the observation vector? Let me just stress that the models trained without augmentation never came across shuffled observations at training time. And we want to know what would happen to their performance if we do shuffle the features. And for this, I had to write some extra code that I'm not going to present in this video. However, you can find it on GitHub. Here are the results. Alright, so this plot investigates how good or bad different models are at dealing with feature shuffling. On the x-axis, we have 6 different models. A small note here, invariant hours corresponds to the model I tried to train from scratch, whereas the invariant official is the permutation invariant model with the weights the authors open sourced on GitHub. The y-axis represents the overall reward. Finally, the 2 colors represent whether shuffling was taking place or not. And the actual distributions were obtained by running 200 rollouts. So if we start from the left, we see the MLP model. Clearly, it is very good when there is no shuffling. However, as soon as we introduce shuffling, it basically stops working. Then we have the MLP model with shuffling augmentations. And here we see that without shuffling, the performance decreases compared to the no augmentation model. However, if we start shuffling the features, the model gets worse, but not by much. This would suggest that the augmentations did make the model immune to shuffling to a certain extent, however, not completely. Then we have the permutation-invariant model, and as you can see, especially the model with the official weights is performing really well, and its performance is not influenced by shuffling the features at all. By the way, let me stress that these results are not comparable to those presented in the paper because we have a different environment that is supposed to be way easier. Finally, we have the linear models, and here we see the same pattern as with the MLP model. Without augmentations and no shuffling, the model is pretty good. However, as soon as we shuffle, it is basically useless. However, the augmentations do make the model immune to shuffling to a certain extent, but not completely. Here we have a closer look at the permutation-invariant model using the official weights. On the x-axis, we have the number of noise features we injected into the observation vector. And the rest of the figure stays the same as the previous one. And quite amazingly, you can see that the model is basically able to ignore the noise features when there are 5 of them. And when we increase the number of noise features, there seem to be rollouts where the model struggles, but still, overall, it seems to be extremely robust to noise. And I believe this is one of the main properties that the authors try to highlight in the paper. It is pretty cool. I guess one could question whether their generated noise was really that hard to spot, since it was sampled independently at each step with a fixed mean and standard deviation. However, I did not really have time to do more experiments. Anyway, this property is definitely impressive and, in my opinion, not obvious. Anyway, that's it for today. I just generated a bunch of videos of the actual rollout, so feel free to inspect them. Let me stress that one thing I did not really cover in this video was shuffling the features during a rollout, which is a more challenging task than only doing it once before the rollout. Anyway, thank you very much for watching this video. And again, I would really like to thank the authors and give them all the credit. I hope I managed to simplify their multi-purpose code. However, maybe I didn't. Who knows? I would definitely encourage you to check out their code too. It is more than likely that my code contains mistakes and misses important details. Additionally, I would like to point out that the authors were really responsive and supportive when I asked questions on GitHub, so I definitely appreciate that. If you enjoyed this video, don't hesitate to like it, leave a comment, and subscribe. This is probably the best way to let me know that you enjoy my content. Also, I'm very open to suggestions and making these videos better, and therefore constructive criticism is more than welcome. Anyway, have a nice rest of the day and see you next time.